It's my pleasure to present you some insights on our ongoing endeavor of developing the neuroscientific foundations of program comprehension. So it's about program understanding, it's about understanding program understanding, it's about measuring program comprehension and identifying the factors that influence program comprehension. So the short title is Brains on Code, and the idea behind this long-term endeavor, it's about 10 years, is, which only recently was funded, is nicely motivated by this quote by Don Knuth, and it's worth the time to read it. So he's saying, let us change our traditional attitude to the construction of programs. Instead of imagining that our main task is to instruct a computer what to do, let us concentrate rather on explaining to human beings what we want a computer to do. So he's talking about program comprehension and making programs understandable. Okay, so, but what is maybe not so known is that program comprehension as activity is actually the dominant activity in software development, in programming. So, so that means most of their time programmers spend on understanding their own code and the code of others. So, but the question is still, so that's fine and good, so why is it relevant to understand and measure program comprehension? And there's, you know, this kind of trivial answer: if you can't measure it, you can't improve it, and we want to improve it, yeah, because that has implications for software quality, for maintainability, and also for correctness. So, but there are more non-trivial answers. So first of all, every software company or large-scale software company and large-scale software project has often rather strict guidelines on how to organize the code, design the code, and so on. And these guidelines often talk about, not always, but often talk about understandability. Yeah? So the goal is to make this code understandability, to avoid bugs, to make it maintainable, and so on. So that's laudable. But if you look into this, it is clear that there's actually not much evidence, scientific evidence, for the choices they make. Yeah? And given the importance, we should work on this. So it's mostly plausibility arguments, but not evidence. So a related topic is, you know, these discussions we love all so much, right, on which programming language is superior in which situations. And there is often, you hear some technical arguments, that's fine, but you also hear a lot about arguments in the direction of comprehension. So you hear arguments like, this is more intuitive, that is more natural, that's easier to understand, and so on. And if you look into these discussions, you also see that there is not much scientific evidence for these arguments. It's again mostly plausibility arguments. So another relevant motivation is that what has been observed in the wild is that there is this myth or species of 10xers. So these are programmers that are substantially more efficient than other programmers. That's why they call 10xers. So there's an order of magnitude more efficient, and companies are really hunt them. And the question is now, what are these people doing? What are their strategies? And can we somehow, if that's possible at all, transform average programmers somehow by training to 10xers or top coders? Yeah, and actually we don't know much about this. And if we want to want to train our children, educate our children to become literate in the digital world, it's of course important to know what they understand and how to train programming. Yeah, so there's many proposals: objects first, functions first, block-based, graphical, teach them many language, teach them one language, teach them just the concepts. Actually, there's not much evidence what to do, really, what is really working. We don't know, there's lots of proposals. And finally, so it's a very new topic, well, with the advent of large language models and neural networks for program generation, the the fraction of the time you spend on understanding code is even increasing. So it is getting apparently easier to produce code, but these large language models, they work in general, so neural networks, generative neural networks work in general in situations where it's easy to verify the result. Yeah? And with this verify I mean not formal verification, but for the people to see, is that the code we want or the text we want. And here's some code I generated with ChatGPT for a B tree, knows this basic data structure in databases in Kotlin. Well, so I would not use this code in production. Yeah? So I would first need to understand what's going on, and you see it's not trivial. So here still the skill of program comprehension and the research on what is understandable is very relevant and becomes even more relevant. So I hope I could convince you now that understanding and measuring program comprehension is relevant. And the question is, how do we do the measurement? And there has been work. There's approaches to do this. So I'm not the first realizing that we need to do it. Yeah? So one important line of work is developing code complexity measures. Yeah? Here the idea is to analyze the structure and maybe also semantics of the program and to put a number on it. And that number tells us about the complexity and by transitivity also about how understandable and maintainable this code is. Yeah? So we measure it and then we can obtain all these numbers. And there are many code complexity measures. So what is known from research, it's still used a lot in practice and even measured automatically. Yeah? Sometimes even patches are rejected just based on those numbers. What is known from research is that actually most of these measures do not tell us much about understandability and also complexity. Yeah, there are studies on that, and especially the most used measures like McCabe's cyclomatic complexity, for example. So it's well known that it does not tell us much about the complexity of code. So I'm not saying that these measures don't work. That's not the point, but they're not the answer to my question. Yeah? So what is done alternatively, especially in research and in studies, in order to understand whether this code is understandable or not? Well, most simply you could ask developers. So have a look at the code. Do you think it's understandable? And we know from psychology that there's always bias. So it's always subjective. And if you think about asking a Haskell programmer about a Java program whether it's understandable, then it's not only the Java program we learn something about, but also about the perception and the preferences of the Haskell programmer. Yeah, so that's a confounding factor. It's not objective. So what people then do to make it a bit more objective is to say, hey, wait, maybe we ask you to solve a task. Yeah, so here's the code, even though you are a Haskell programmer, here's Java code. So what is the output of this program, for example? Yeah, where's the bug and so on? And then you could do this with different people, and you could record these external observables like task correctness and completion time and so on. Yeah? So that's also done a lot. And in general, so we have these two worlds, right? We have the programmer and the comprehension task on the one hand, and when we have external observables, yeah, like task completion time, even subjective assessment and so on. And there's a gap between the two. Yeah? So what we want to do is to infer, based on the external observabilities, something about the property understandability of the code. So if you observe that the people working on Haskell code are faster in general, on average, or whatever, then we would like to attribute this difference to the fact that it is Haskell code and not Python code. Yeah? These are just examples. Could be also the other way around. The point is, we don't know, right? Because there are various confounding factors. It could be just that, like the Haskell programmer does not like Java. Yeah? It could be programming experience. It could be personal preference. It could be just noise, yeah? Interpersonal variance in doing things. So, and there's various confounding factors, and this is especially the presence of these confounding factors is the main obstacle in program comprehension research. You never really know what really the factors are that influence program comprehension. It's very difficult. And that's where our endeavors started. So we would like to repeat the success of leveraging methods from cognitive neuroscience in other disciplines here in this setting, in order to pinpoint the factors that really matter for program comprehension and to connect these two worlds. So we're not throwing these external observables away. We're still looking into whether they solve the task correctly or not. So that's in addition. So, and that's basically leads me to the second part. So here I would like now talk a bit about this idea of this project that was recently been funded. So on top of that long-term endeavor, Brains on Code, that was funded by the European Union and by ERC. And instead of going over a research questions and a research program, I would like to explain it by example to give you an illustration how we work in this project, how we worked in the past and how we will work in the future in this project. And the example is here, we ask a simple research question and then I show you how we address it. And the research question is simple, just to fit it, to make it fit here into the presentation. So the question could be, do meaningful identifiers like program variable names or function names facilitate program comprehension? And then you could say yes or no, but we don't know. So actually we know, but you could come up with a hypothesis. So what we do is, and that's pretty common in this area, right? We create code snippets and tasks for with meaningful identifiers and meaningless identifiers. And then, of course, you can talk at length what meaningful actually means. And then we give it to various people in a very controlled setting, and then we see how they solve the task. So in terms of correctness and task completion time. So let's say we find that with meaningful identifiers, the people are faster or more correct or both. So the question is now that we ask, is it really the meaningfulness of the identifiers that made the difference? And here in this project, we measure various neurophysiological properties like the activation of brain areas, the general mental state in terms of cognitive load, but also where the programmers look at, in order to learn whether it's really the meaningfulness, and it depends of course on the research question at what we look, but here we look whether it's really the meaningfulness of the identifiers that made this difference. To be sure. It's a form of triangulation, if you want. What we also do in this project, and I'm not talking too much here about it because we are quite early, we would like to build, to do theory building. So it means we would like to have a cognitive model that captures the relation between the stimulus, the external observables, and also the brain activation and so on. And based on that, we of course would like to establish a cycle and say, well, we have a new hypothesis based on this result. So maybe it's not the general meaningfulness, but it works only for some identifiers and if this and that. So that's a new hypothesis, and then we need to create a new experiment. And what we also want to do is, of course, to give back and maybe make suggestions for programming guidelines and education in this case. So that's the general idea. For this purpose, we need to work on the methodological foundations. That means we need to create a multimodal experiment framework that integrates different modalities, functional magnetic resonance imaging, EEG, eye tracking, and so on. I will give later more details on that. And here, the problem is really to bring all of them together. There's lots of technical and conceptual problems, in a sense, beyond program comprehension, but we still need to solve them, and we're working with neuroscientists to do this. That's very important. What we also want to do is theory building. I talked about this. Here specifically, we work on a computational cognitive modeling approach. So specifically, we want to use ACT-R. So that's an existing, very successful approach. So the idea is to model program comprehension as a process, as a cognitive process in terms of the basic perceptive and cognitive operations of the human mind. And we would like to use these models to simulate program comprehension. So that's what ACT-R can give you. right? These models make, based on a certain stimulus, statements and predictions about the task completion time, and also it can be connected to fMRI data, so it can make predictions also about the brain activity. And now the interesting thing is that actually we need to effectively align the empirical observations, so the actual brain activity and the actual task completion time with the simulation, right? And if these if these two worlds agree, then that's a step forward in our understanding how the process works. ACT-R has been successfully used in other disciplines, for example, in natural language understanding. So that's why we are at least have the hope that it works for us. But program comprehension is really a distinct semantic, multifaceted cognitive process, and it's not clear whether such a complex process can be really modeled. So that's in a sense a risk here, and that's what these people at ERC also like. You know, it needs to be risky, and I think we are not very far at the moment with that. And finally, just to wrap it up, what our intention is, we would like to install this feedback loop. So we want to have a scientific feedback loop based on empirical falsification. And for that you need experiments, you need theory building, and you need, well, test these results in the wild with regard to programming, methodology, language design, and education. And that's also what is missing, by the way, also in many other areas, establishing such a scientific feedback loop. And it's obviously non-trivial to do this. So it's kind of a long-term goal. Okay, so after this brief overview of how we work, I would like to dive into a few more details in order to later for you to understand our results we obtained so far. So I will specifically talking here about one modality or one measurement method, which is functional magnetic resonance imaging, and I like this most, and we were also pioneering this method, using this method in this area of program comprehension. So EEG has been used before by others, and we use it as well, but here for now we talk about fMRI. And what you do is basically you, and that's very fundamental, so like the name of the conference, there's very fundamental research. You put people in fMRI scanner and you let them understand code, you let them solve code comprehension tasks. That limits ecologic validity quite a lot, but it gives you fundamental insights. And the scanner is then recording the brain activation, and we all know these nice pictures, right? There's brain and somehow there's highlighted areas, so that's the activation. But what was not clear to me for a long time before we started was that what is that actually that is measured there? So what is brain activation? And just a short explanation, so in fMRI you are measuring the BOLD response. BOLD means a blood oxygen level dependent response. And here the idea is that activity in an area leads to a rise and decline of oxygen. Because in order for an area to be active, it needs more oxygen. So what you see then, so what neuroscientists see in the brain is that you have this time-dependent function where you start with inactivity, there's not much oxygen in the blood, then the brain area becomes active, then there's more oxygen in the blood, and then it declines at some point. And it's a very characteristic function which is called the BOLD response. And the point is that blood with lots of oxygen has different magnetic properties than blood without oxygen. And that's basically what the fMRI scanner is doing, and I think there was also a Nobel Prize involved in this, of developing all of that. Of course we didn't do that, that was developed in the 90s. And then activation is basically kind of doing statistics and seeing where these responses are in the brain, and then you get these figures. There's lots of details. Okay, so at this point, when we understood this, we say, well, we are ready to do the thing, right? So let's show programmers code and record the activation, and then we look into the activation, and then we learn about programming. But it's actually not so simple, and that's what we learned the hard way. Yes, the problem is, so if you show somebody code and then record the brain activation, you always observe an activation, because the brain is always active. Yeah? So people are basically alive. And so the question now is, well, which part of this activation is actually related to the very act of program comprehension and which is not, which is related to something else. And yeah, so it was not really clear to us in the beginning that this is actually a key problem in research in this area. And what people invented already in the 19th century, I guess, in psychology, but then used later also in neuroscience, is the subtraction method. Yeah, so here the idea is, well, you record the activity with a program comprehension task, and then somehow you need a second task, which is very similar, except the very act of program comprehension. Yeah, but the rest, the setting and so on, is very similar. That's called the control task. Yeah, you have that in many neuroscience experiments. And then what you want to do is to subtract the two. And then the hypothesis is, and that's used in thousands and thousands of neuroscience experiments, the hypothesis is that, well, then this resulting activation is just related to the very act of program comprehension. So here it was actually to us to do our first contribution. So what are valid and useful control tasks in our settings? And we started we tried many, and our first one, and nowadays we have others, but our first one that worked well and that has been replicated in other studies and so on, is spotting syntax errors. Yeah? And while I'm talking, I guess some of you already spotted some. And the task is here really for the participant, so spot syntax errors as fast as possible. And the hypothesis is that for this task, you actually don't need to understand the program. You don't need to compute the output in order to see maybe not all. It's also not important that you catch all. Important is to bring you in a state where you search for syntax errors, and then you do something like program comprehension, except that you really don't need to understand the program. And here are a couple of syntax errors in. Yeah. So, okay, so that was our first control task. In the meantime, we have even papers on, comparing different control tasks and so on. But just to give you more illustration how that really works, so all of our experiments with fMRI have been conducted at the Leibniz Institute for Neurobiology in Magdeburg. So the first one was in 2014. And since then we are doing our measurements there. And just to give you an illustration how it works, so typically you show a sequence of snippets. You have an experiment protocol, and there's different, depending on the research question, you have different protocols. Here, let's do a very simple one. We have a warm-up task. Comprehension means basically, and of course you need a briefing procedure to explain all of that before the experiment, right? So here, comprehensive code, it's a warm-up task. So it's actually not super interesting. Then you have always a rest condition to try to understand what the rest activation in the brain is in order to compare later. Then you have a syntax condition. So where's the syntax error? Rest condition. Then you have an actual comprehension task. So what is the output? Rest condition, syntax task, and so on. And depending on the research question, you have different kinds of tasks. You have, I don't know, the Haskell task and a Java task or whatever task. Yeah? And then you do this with different people, and you also, depending on the protocol, show different things to different people. Yeah? Not simultaneously, but can only be one person in a scanner at a time, of course. And that's how you do your studies there. And there's also lots of work in designing these protocols. So, and at this point, we also thought we are done. Yeah, now we can look into these activations and see what the difference is. Yeah, but it's actually not true. So there's quite some heavy data processing involved, which we basically take from the neuroscience world. Yeah, we are not inventing, statistical algorithms to process data. One interesting fact is, and that's important to know, so most of the time when you see these pictures in, say, in the news with activations, it's actually an aggregation over tasks and participants. Yeah, it's not a single person, it's aggregated. And nowadays there are also studies not doing this with different pros and cons. Yeah? But if you aggregate over participants, well, the problem is there are anatomical differences, yeah, and much more than you think. So what is done in neuroscience is you transform the data to a standard brain with a standard coordinate system, which is called a Talailach coordinate system. There are also others. And then even this coordinate system is spatially separated in chunks, which are then have names and numbers and so on. These areas are called Brodmann areas, and they have numbers. Okay, so and then there are other things involved, like motion correction and whatever. Yeah, so it's actually quite some heavy statistics going on and a bit of information processing. So, but now let's look at a couple of example results after this procedure. So here is an example result for a program comprehension task, aggregated, processed, and everything. And what we get basically is coordinates, which are these x, y's, and z's. We get a cluster size, so it's the volume basically of the activation. And we get automatically from the tool, because it's in a setup of a comprehension task, you get the Brodmann area, which is basically a number. And later we will see what we do with these numbers, right? But for now, it's important to understand that, well, it's not just activation or not, but you get also the time-resolved signal seeing, so how the activations changed over time. Yeah? And this information will become important later. So in a sense, the last task is to map these activations, which are assigned to Brodmann areas, to cognitive processes. So that's basically, again, say like 100 years of neuroscience and psychology research, where you then can try to map function to activation. Yeah? So you know there are things like language processing areas and so on. Okay, maybe a few words. So I talked a lot about fMRI now, but I said we want to have a multimodal setup. So what we have in our setup is we have this fMRI scanner at the Leibniz Institute, but what is possible there, and we worked on this, is we can put in participants with EEG caps. And due to the strong magnetic fields in the scanner, that needs to be very special EEG caps and everything. There's all kinds of interferences and so on. But that's possible. We can simultaneously measure fMRI, so brain activation with fMRI and EEG, which is measuring basically the electric current on the brain surface, which tells you, for example, about the cognitive load about the person. I will give you later also an example on this. Of course, we need to show, so there's an EEG cap, we need to show people something. So there needs to be a screen and a projector, and all of that needs to be without materials, without materials that have magnetic properties. So otherwise people can really die. So it's very strong forces. And people died before because somebody forgot a chair in the room and everything. Yeah? It's super strong magnetic fields. But if there's nothing magnetic, you're safe. Okay, and then you need to do eye tracking. Yeah? And the eye tracker itself has magnetic properties, so you need to put it outside, but then you need a mirror inside in order to get the bright signal. So you can imagine that there's lots of details here and lots of technical challenges. And there's even a paper in a neuroscience or neuroimaging venue explaining the setup, and where one of my students were involved. So, but it's not program comprehension research. Yeah? So that's neuroscience stuff. But we need this setup in order to do our work. And based on this, you get all these signals, and now you need to make sense of it, right? You need somehow, that's what I was saying, right? You need to have a multimodal setup, and you need to do multimodal data exploration. So what we developed, and I think that's very cool, especially one aspect, is we developed this dashboard, which you can use to explore an experiment that has been conducted in the past, to learn about where the participant looked at, what the brain activation was at this time, what in general, which areas were activated. But you learn also about the heart rate and respiration, all of that. It tells you something about the mental state of the participant. And the most interesting thing is really here, is this a slider. So I like this a lot, because with the slider you can go back and forwards in time. Yeah? So we are after the experiments, and we can, with that go back to different points in time in the experiment, and then compare, say, where the person looked at, what was the activation in which area at this time, and was the heart rate up or down, and things like this. So that's very important. It's in a sense also, especially when you integrate also EEG, it's also an innovation in this area. Yeah, so people did not have that for most of the time in neuroscience. Okay, so that's basically a few details on, well, which challenges we had and how we solved them. And now I would like to use the remaining time to talk about the results we already got. So as I said, it's a long-term endeavor, but it is ongoing. So these are, in a sense, a cherry-picked results. So it's lots of try and error going on, especially with the setup. And then you have high dropout rates. That means so the data are useless, but still you spend the time and the money, so it's actually quite expensive to do these experiments. You spend the time, but then the data are useless and so on. So you need to have also good skills in helping your students, going through this phase. But here are some interesting, or some results that I think are interesting. So let me first have some water. So the first result we got, and I think it's pretty important, but I need to explain it, is we found in 2014, and it was confirmed later a couple of times, that actually program comprehension induces a left-dominant activation, which is very related to language processing. It's very similar to language processing, what's going on. And you'll see that from the brain activation. The point is, why is this an important first result? So actually, nowadays people say, well, yeah, programming language is a language, so it's language processing is going on. But when we started, there are actually a couple of more, so there were hypotheses regarding a couple of more cognitive processes, logic, problem solving, mathematics, whatever. So that's actually many more candidates, but we found a clear signal that points to language processing. And our neuroscientist in the team was actually surprised that we get such a clear and localized signal in a first run. So it's also not common in neuroscience studies. So typically you get a chaos of different activation patterns and nobody knows what it means. So here it was very clear and it has been replicated. And interestingly, it is again relates to an old statement, here in this case Edgar Dijkstra, who was saying, I don't know, in the 70s, so actually we need to teach our programmers more natural language skills. Yeah? And it's somehow nobody listens. So if you look in our, say, programming education and in the university and in school and everywhere, so we are not paying attention to this. And I have the feeling that, say, at least the population of computer science students I know, compared to the general population, they're not the best in natural language skills, yeah? and using natural language. So, but our results actually point to this. So can you somehow improve language skills and with that also improve the skills in programming? So that's basically the next hypothesis. And at the time, and that's more of an interesting side story, at the time, so 2014, there was also this news. And that was a coincidence with our results. So here in 2014, the state of Kentucky, and that's really true, decided that computer programming would satisfy foreign language requirements in school. So it means that as a student you could kind of exchange Spanish for C++. So I mean, we provide some evidence that similar skills are involved. But, well, personally I think that learning a natural language is also learning about the culture, so I would like to learn about the culture of Spain, but maybe not of C++. Yeah? So, but it's an interesting side story, which we, and in the meantime also other states like Iowa and so on put out such a bill, so it's really true. Then we moved on, so we kind of started to test our methodology in different settings, and here we attacked a fundamental question from the 70s and 80s in program comprehension research. So there's the hypothesis that there's actually two strategies in program comprehension. One is called top-down comprehension, the other is bottom-up comprehension, and that they are different. Yeah, there's different strategies. So in top-down comprehension, you start with some semantic cue or semantic piece of information, maybe also a syntactic piece of information. So here in our code, for example, the name of the function, reverse word, and the human being or the programmer is using it to form a hypothesis, what this code is doing. And then he's going down into the code, or she's going down to the code in order to confirm this hypothesis. So that's top-down comprehension. And it is deemed that this is more efficient than bottom-up comprehensions, where you do not have this information. And you go through the code in the absence of useful information. You go through the code and, you know, statement by statement, expression by expression, and then you form chunks in order to create a higher level understanding of what's going on. There's different factors that facilitate or that are deemed to facilitate top-down comprehension. But actually we don't know, yeah? So what we wanted to do is it really the case, and we observed that people with top-down comprehension are fast and correct. But is it really the case that these are different processes? Yeah? So that's how the literature is. There are very different processes. One is more efficient, and we wanted to learn what the neurophysiological basis for this observation is. So we did an experiment, and actually, and that's very interesting, we found, and that again was not necessarily to be expected. It's the same areas involved. So it's not different areas involved. So it could have been that, you know, some areas related to storing domain knowledge, whatever, are involved in top-down comprehension. But it's not the case. We have actually a similar activation pattern. So in the brain, very localized and clean. But the question is why they are different. Why are people faster? And what we found is that actually, and here's the plot, and actually it points to the fact that people with top-down comprehension are more efficient. So what's called neural efficiency. There was the same activation, but with a lower magnitude. The blue is then the top-down, and the red is the bottom-up. And that's called neural efficiency, and it tells us that in top-down comprehension you use the same areas, but with less effort. And later we will triangulate this result. I will come to this in a few minutes. But that was kind of an interesting result, and we complement it later. In a third experiment, now in going over these results, we found an interesting experiment we did, and I like it a lot, is we wanted to learn, so what is it really about code complexity? Metrics. Yeah? So what we did is we compared two sets of code. So there's so many code complexity metrics, but we categorized them. So there's of course trivial metrics that count the number of lines of code, things like this. But there are more sophisticated code complexity measures that are based on the control flow. Yeah, they create a control flow graph and then they count something. And depending on the metric, it's a number of branches, a number of cycles, whatever. And McCabe's cyclomatic complexity is also in this category. So there's a couple of metrics in this category, or measures. And what we did, and I think that's interesting, is we looked into recent proposals of metrics that say, well, hey, so maybe it's not the control flow that's telling us really about the complexity of a program, but it should be also data flow. That means if there are many variables whose values depend on other values that are then computed and so on. So maybe that's an interesting measure that tells us about the understandability of code. Yeah? So, and then you can count again the number of edges in the data dependence graph, or the lengths of paths, and there are many possibilities really to come up with a measure. And here we used especially depth degree, which was proposed actually by Dirk. He's not here anymore. 10 years ago. And now what we did is, so we wanted to see if the metric is a predictor for cognitive load in the brain. Yeah? And if it's a predictor, then it seems to be that it tells us something about the complexity of the code, right? And predictor means, so if the metric says, well, it's complex, then we would like to see in the brain also, high cognitive load. And if the metric says it's not complex, then we would like to see in relation also a low cognitive load. What we also found before that is that that somehow data flow tells us more about these external observables, so correctness and completion time, but the brain activation was actually more interesting. So long story short, so what we found is that no control flow based metric was a good predictor for cognitive load. And actually, depth degree as an example of a data flow based metric is actually a better predictor, or is a predictor at all, which is significant. So I think that's a pretty cool result. So it's not that we're kind of proclaiming the truth here, but it's now it is at the rank of a hypothesis, saying, well, it seems that data flow based metrics are really telling us more about code complexity, and now we need to set up new experiments to replicate this result and to check it, yeah, because then there are different metrics, different code snippets, and so on. Yeah, we will need to go more into this detail. But I think that's actually a success story of this project. In a sense, showing what is possible with this methodology. Okay, so we looked also at many more of this whole zoo of complexity metrics, but almost no show any significant relation to cognitive load. Yeah. Okay. So now let's get back to our idea of combining modalities. Yeah, so far we looked only at one modality at a time, but actually can use multiple modalities to learn more. So let's get back to this meaningful identifier and meaningless identifier example. So here we found a difference in the activation, which points to the fact that the meaningful, or which kind of triangulates or confirms the fact that the meaningfulness makes a difference. So now the question is actually, so it's happening here, say in this time development, in this time course of the activation, but the question is, and I did not talk about this deliberately, because the question is, well, there's also other differences between these pieces of code in addition to the meaningfulness. So it's, for example, the line length is different. So is it really the identifiers that makes a difference? So what we did is and that's super interesting, we used eye tracking, we recorded eye tracking, and we're really able to triangulate this result and map the eye pattern, so looking at identifiers at the time of the difference of the activation. So now these two results together provide us with more confidence. That's really here's the difference. So need to hurry a little bit. Here is an experiment with EEG, and the important thing is not EEG, but the important thing is that we varied experienced programmers, so we varied the factor of experience. We have experienced programmers and novices. And we would like to understand whether the experienced programmers are more efficient, so that's an external observable, but we wanted to know whether that also makes a difference with regard to cognitive load and code reading. The very fact that you are experienced and not top-down or bottom-up. Yeah? And for that we use EEG, which can tell us about cognitive load. That's all you need to know at this moment. And actually we found, and that's seen in this plot, we found the relation between more experience, higher efficiency, which is basically correctness per time, and lower cognitive load. So on the y-axis you have the time course of the experiment, on the y-axis you have the cognitive load, and each line is a participant measured. And the color code tells you about the efficiency. So what you see is that the lighter colors correspond to experienced programmers that use then at the same time have a lower cognitive load, confirming this result. And that was also not clear because maybe it is not the cognitive load that differs, but the use of brain areas that is different. What we also found is that we wanted to know, so why is the cognitive load different? So we found basically that experienced programmers have a totally different reading strategy of the code, which leads to this lower cognitive load. So they are more, that's what you see on the right, they go more targeted to the code and arrive faster at the conclusion as compared to novices, which is then not too surprising, I think. And there's also other eye tracking results on this. A recent result is, where we use then also fMRI in the same setting, is that brain activation-wise, experienced programmers have a different, there is the same brain areas involved, but it's more localized. So experienced programmers have a very much more localized activation in Broca's area, which is a key area in language processing, than novices. And that's a result that resonates also with results in music, sports, and chess and so on, where we know that experienced golfers, for example, have different activation magnitude and a more localized one. And novices kind of need to involve more brain areas and so on. We see that also in programming. And the interesting thing is that it's again language processing. It's the language area. Okay, so the final result before I'm wrapping up is, and I think it's the most important one. So most of these results I've shown you have been replicated by us and by other groups in the world. So we think that we have, at least for this stage, a sufficiently validated methodology. And I think that's one of the most important results, maybe. But maybe it's least exciting, but that's actually very important. Just a few final thoughts. So where do we want to go? And I think it's now, it should be pretty obvious what we want to do with this, right? So we would like to know what makes a program hard to understand. So which properties of the program. We would like to come up with a method to reliably measure program comprehension. At the moment, we just have results in different kinds of settings, but we do not have a validated measure yet. We would like to look into programming mechanisms. So what are the trade-offs between expressiveness and understandability? So for example, well, you have in functional programming higher order functions. You can very concisely explain what's going on. But how is it for experienced and non-experienced programmers? Is that expressiveness, does it come at a cost, and so on? So it's actually not clear. So you get many opinions, but it's not clear. What constitutes programming expertise? Actually, we don't know at all. Yeah? So do we need to know about many languages? One language a lot? General intelligence? Concepts? We don't know really. Well, then also, how do we teach children? I motivated this. And a recent thing, we started with the advent of these language models is, well, so actually we need to train these models to generate understandable code on the one hand. It's not so clear how to tell the tool, yeah? I mean, you could ask ChatGPT to make it understandable, but is it? We don't know. And on the other hand, it's somehow these language models capture the knowledge of all the code in the world, so maybe we can use them also to understand better what understandability is out in the world. Yeah, but that's really speculation here. Okay, so it's a team effort. Of course, here in alphabetical order, the core team, so of the last 10 years, and further contributors. And with that, I'm done and ready and happy to take questions.
Thanks for the nice talk. So you said you conducted results with different programming languages. I wanted to ask whether the results you presented here were one specific one or whether they were kind of the same with different languages. And
so we did not look yet into this rabbit hole of functional versus or Rust versus something, or Haskell versus something. That's more for motivation. We want to do this, but the actual point is if you vary the programming language, then you still need to have comparable tasks. And it's actually not so trivial to design a task in Rust and Haskell simultaneously without being biased towards one language. So actually it's more about what kind of task is somehow more intuitive, and then you put in a hypothesis for which language. And I guess that's really the way to go. I mean, there are studies from a befriended group in Michigan which looked at recursion versus iteration, so loops. And the thing is that you use recursion more in functional languages and loops more in imperative languages, but it's just a pattern. And then they looked into this issue. But well, that's actually more difficult to do this. But I use it for motivation because people are so emotional about programming languages, and always everybody comes with their pet example where this language is better than that, and so on. But it should be very interesting to do experiments in this direction. Yeah.
Thanks for the fascinating talk. I was wondering if there is a interest for placing the program understanding in the context of the process development, of the development process, right? Where the program comes with maybe additional information like requirements, architecture, detailed design, or even comments. And what insights can we draw from that?
Yeah, we do not have insights on this. So in a sense, we needed to start with this project to set up the methodology and to focus on code. But so actually what you would like to do is to go more and more into the whole practice of software development. So at the moment, it's just program comprehension. So it's not, you know, using fMRI to understand software development in general. But it's, I think it's easy to imagine that you could come up with very interesting experiments where you have code and somehow a specification or requirements. And then you could argue, well, which presentation of the specification helps actually for the person to check whether, or which kind of formulation of the requirements helps to validate it for the person, whether it's really implemented or not, or with test cases and so on. So there's many things you could do. But again, so at the moment, we need to increase internal validity. Yeah? So we need to be very controlled, which harms external validity and ecological validity to a good extent. But so our choice is to start with an internally valid setup in order to control things, to form hypotheses, and then to broaden. That's our trajectory.
Yeah, thank you very much for this very nice talk. There's another dimension to this, which I guess you could not at the same time address as you address all these other questions. But I wanted to have your take on that. It's one thing to understand something, and it's another thing to think I understand something, right? So for instance, these code co-pilots, they give mostly quite beautiful code and makes a lot of sense, and you think, oh, this looks nice. I think I understand it, but I may not.
That's right. So I mean, that's actually. Let's put large language models aside. Even in our experiments, we need to make sure that people understood something. Otherwise, we cannot relate the signal to this fact. Yeah? So that's why you have actually to do a lot of task engineering. So how can you set up a task that you really know that the person knows it? Yeah, and there's computing the output, but you could also say where's the bug, where's the syntax bug, and so on. And that's really where we go methodologically. So in the practice of programming, if you use a large language model, well, maybe it's not very different from looking at the code of somebody else. So you need to verify it. And well, so here I could imagine to use this experiment set up in this direction, but that's a key problem. Yeah, so yes, it's an important question, but it's a bit orthogonal. It's actually a side comment. Yeah, so we in designing these tasks, it's always a challenge to make sure that the people really do what you want. Yeah, and that's why a rest state activation is not enough, because people could suddenly start to plan their meals. Yeah, and then you see that. So that's really, if you want to reject such a project, it's very easy. I can tell you many things how to reject it, because it's complicated. Yeah.
Thank you for your talk. Do you know what is the specific usefulness of the broca's areas in language processing, and how it's related to program understanding?
Yeah. So I mean, the point is that broca's area is one of the key areas in language processing, and somehow. I mean, now, so I'm not a neuroscientist. I can just give you my information, what I learned from my colleagues, right? So what the brain is doing, so there's these evolutionary trained language areas for language, for example, and then we face new challenges, right? New tasks, and we cannot evolve. So computer programming is not around for a long time. So what the brain is doing in all these tasks in the modern world, it is reusing areas. Yeah? And here it's a clear thing that it's mostly, especially an experienced programmer, mostly using the area of Broca's area. Yeah? And so actually we need to do more research on this, but that's a surprising result. It could have been something else. Yeah? So a study we think about, and I mean, you might ask why we didn't do all these studies. So first, it's very expensive, and it takes a year to do such a study, yeah, with all the preparation, and then getting people be willing to go inside the scanner and so on. Yeah, so what would be interesting is then to, and a colleague of mine, also part of the team, Janet Siegmund, is working on this, is to train people in a controlled setting in a longitudinal study, language skills, and to see whether they perform better in programming, and also see a related activation in the brain. So that would that experiment would shed some light on this question. Yeah, so with that you could say here's really evidence that training language skills, and there's standard training methods in linguistics. So it's not, we do not need to invent it. There's standard methods to have like over 6 weeks or 6 months. There's different ways to train people in language skills. And then you would like to do the experiment, but that's all very difficult. So in such a setup, you need to have participants going into the scanner, then do 6 months your stuff, and then go in the scanner again. Yeah, so we are working on this, but it's very difficult.
It was very interesting how you control in your studies for varying factors. And I was wondering if you try to control for the emotional state. For instance, if I were shown a program with lots of identifiers that do not make sense, I think that for a fraction of a second I would feel annoyed and a bit, maybe a bit angry about that. So that's right. How do you control for that?
I mean, yeah, that's true. So that's why we have, I've hinted at this in this Coda's Muse dashboard. So you also record other things like skin respiration, heart rate, and so on. And that's a main driver also to contextualize results. So if you have an outlier in the data, then we also cross-check and see if maybe it's a person who was very scared in the scanner. Yeah, so that happens, and that's where these high dropout rates come from. Yeah, dropout means you recorded data, but you cannot use the data set, and the dropout rate is very high. So that's the normal thing in neuroscience. So sometimes you have 50% dropout rate. So, and that's because of that. You need to be, in a sense, you need to be honest, yeah, here a lot. So you can, which means conversely, if you are not honest, you can cheat a lot, and it's hard to detect this, yeah, because well, if people really need to look in the data, and yeah, we try to be honest, but you need to believe me. Yeah.
We have a last question here.
Thanks, Sven, for the nice talk. I'm here very far. Yeah. So this community is obsessed with program correctness, I would say.
So I realized this.
A trick we often use is dualizing these questions. So, I mean, we also obsess with program incorrectness. So I am interested in Neuroscientific Foundation of Program Incomprehension. So is that a thing at all? So I think it would be very useful for us to understand what people don't understand and why.
Yes. I mean, somehow some of the results you could invert, but actually that's very interesting. There's this line of work by people from New York City University. It's Dan Gopstein, for example. So they came up with this idea, also with high internal validity of atoms of confusion. So it's a bit steered to imperative languages, but they said, so these are the undividable pieces of code that cause confusion and lead to bugs. Yeah? It's just one source of error. Yeah? There's these large-scale logic errors and so on. You think of the C language and, you know, post-increment, pre-increment, and so on. And they did lots of studies actually on this, and we are at the moment, we are doing a sophisticated EEG study, which is then not just measuring the cognitive load, so we are designing it, so it will take place. So if you want to travel to Saarbrücken, it will take place in summer. What we are doing is we measure fixation-related potentials. So it means based on where people looked, we know where in the EEG signal these potentials are. It's not just about cognitive load. And then we know from linguistics that there are different characteristic signals for misunderstanding, confusion, surprise, and so on. And what we would like to do is to triangulate their results, which are based on external observables. So with atoms of confusions, actually they don't know what they're doing. To triangulate these results, and with that also to relate our methodology to all this nice work that has been done in cognitive linguistics. Yeah, so where they talk a lot about long-term relations in sentences, surprise, and so on, and that plays a very big role. So yes, much of our work can be steered into the direction of incorrectness, that's where these communities come together. Yeah, we should.
Okay, thank you very much again.
Thank you.